higher crown-to-implant ratio associated with short dental implant length, and potentially it leads to increased local stresses on the bone. We know that well-distributed functional loading on the implants is beneficial for promoting osseointegration, but excessive stress and strains can lead to irreversible biological and structural damages, such as the loss of the peri-implant bone, implant fractures, screw loosening or fractures, superstructure failures or decementations. And the impact of occlusal overload becomes even more pronounced in cases of poor bone quality, inadequate bone volume, poorly designed prosthesis, non-ideal implant number and positioning, as well as in patients with parafunctional head. So it is crucial to carefully consider factors that could lead to overloading to ensure that the implants and the restorations can handle these loads in a way that is biomechanically appropriate. And this relies on using appropriate methods to analyze the stresses on biological systems. Finite element analysis has been introduced in in implant dentistry to study how stress is distributed, how materials deform, and also to identify the potential failure points in the complex structures such as prosthetic components, implants, and surrounding bones. So this is a numerical technique that uses mathematical functions to solve and quantify mechanical problems. The software creates virtual 3D simulation models by breaking down the problem into smaller elements, forming a mesh of up to millions of tiny elements that represent the structure being analyzed. And the calculations are performed for each element using partial differential equations, and the results of the simulations are typically visualized using color scales to present stress distribution across the object. And these simulations are also valuable for predicting how a part or assembly will behave under certain conditions. In our research, we focused on the biomechanical aspects of short implants for restoring the posterior segments of the atrophic mandible. The goal was to create and validate 3D finite element simulation models based on micro-CT tomography, and to investigate the biomechanical validity of different configurations of a specific clinical scenario, which was the 3-unit screw retained prosthesis supported by 2 or 3 short dental implants in the posterior region of the mandible. The main objective was to collect data that could assist in the clinical evaluation of implant configurations to prevent biomechanical failures. The study involved, as I already mentioned, the establishment of FE models representing atrophic mandibular sites using fresh human cadaver specimen, and these sites were restored by short implants to support 3-unit zirconia prosthesis and to simulate various configurational effects. The study variables included implant length, implant number comparing 2 to 3 implants, prosthesis design such as single crowns, implant bridge, and splinted crowns, and also loading direction comparing vertical to tilted or oblique loading. The model construction process began by capturing the precise bone geometry of the bony specimen using micro-CT to create the bone tissue design, and in the next step 3 Straumann implants were placed in the specimen following the sequence of 8 mm, 6 mm, and 4 mm from mesial to distal to replace the second premolar and first and second molars. So these positions of the implants were digitized using an intraoral scanner for the CAD/CAM fabrication of the zirconia prosthesis, and subsequently a follow-up micro-CT was conducted to reconstruct the 3D surface of the implants, and the prosthetic construction was based on the STL files from the intraoral scan. So all processed images were integrated into a simulation model using software. The model was transferred in a network of tetrahedral elements with defined mechanical properties for each simulated material. Models were assumed to be isotropic, homogeneous, and linearly elastic, and the outcome parameters included global stiffness, local stress accumulation, and strain energy density accumulation. In our initial paper, we focused on assessing the predictive accuracy of the finite element analysis by conducting a comprehensive study that combined mechanical testing with numerical simulations to validate the findings. The restored bone specimen was embedded in a polymer and affixed to a testing rig for mechanical testing. Altogether, 18 different configurations were loaded in a static manner, axially and eccentrically at 100 Newton, and the resulting displacement of the bone implant prosthesis complex was recorded using an optical deformation tracking system to calculate the overall stiffness. And the same loading tests and the boundary conditions were performed on the FE models, and the simulation results were compared with experimental data using linear regression analysis. So as we see here by the results, the overall average correlation of the stiffnesses between the experiment and the simulation showed a high correlation factor of 0.8, but the FIA stiffness was 7.2 times higher and showed a dependence on the test configuration, which was highest for the splinted prosthetic design. So the present numerical model was shown to be able to predict the biomechanical relationships of the tested parameters with a high quality, but without reliable reproduction of the absolute values. So building on this foundation, we moved forward with in silico analysis to examine the biomechanical impact of the previously mentioned configurations. So here we calculated and compared the global stiffnesses, also local stresses within the bone prosthesis and the implants to analyze the stress distribution, and also calculated strain energy density to understand the physiological energies within the bone tissue. Force distribution within prosthesis was used to illustrate the patterns and relationships between the configurations, and the results of this study are detailed in our second publication, revealing that splinting adjacent short implants through the prosthetic rehabilitation and achieving one-to-one replacement of missing teeth have the most significant impact on the magnitude and distribution of local stress peaks and should be considered in the clinical treatment plan. So the research findings have shown that finite element analysis can effectively predict low distribution, bone yielding, and local stresses, also confirming some of the existing stress management theories, but there are also some important factors to keep in mind. One crucial point is the impact of uncertainties and also model parameters on the complexity of modeling tasks. For instance, the simulation of bone tissue properties like anisotropy and heterogeneity, as well as the behavior of dental materials, including plasticity and viscoelasticity, remain a challenge. Another consideration is the simulation of interface conditions, where the majority of in silico studies, including also our research, assume perfect integration and bonding without really accounting for the potential micro-motions at mating component interfaces, which obviously impact the links. So addressing these limitations and improving the quality of simulations requires further research and development. There are already some exciting new directions emerging to push the boundaries of the current modeling practices, such as parameterization of computational models to reflect individual clinical scenarios, also the incorporation of bone remodeling algorithms to evaluate the influence of implant loading on bone adaptation over time. Also the multi-scale modeling to consider the biological response of bone at different levels, and of course the AI-supported modeling with the hope to improve the accuracy of simulations and to optimize material properties. So there is still a lot to do. Thank you very much for your attention.
Thank you all the presenters for their great presentations, and we want to have now a coffee break, and afterwards then we will continue. Thank you very much for your time.